So today we will talk about moment of inertia. So if rho is the constant continuous density for a lamina which is bounded by a region R with an area of A, then the moment of inertia with respect to the x-axis is going to be given by I sub x equal to antiderivative over the region R y square times rho xy dA, whereas the moment of inertia with respect to the y-axis is going to be given by antiderivative over the region R x squared times rho of x comma y dA. And the coordinates for x double bar is going to be iy over m, the square root of that, and y double bar is going to be square root of ix over m. Using these formulas, we are going to find the moment of inertia and x bar comma y bar double bar for some known geometrical surfaces. So let's go to our problems for today's class. The first problem is verifying the given moments of inertia and finding x double bar and y double bar, assuming that each lamina has a density of rho equal to 1. So again, we have fixed the density at 1 gram per square centimeter. And the regions are common shapes used in engineering, and this one is a rectangle that we want to understand. So let's see. We are going to get the rectangle in the first quadrant. And recall that this rectangle actually doesn't have to do anything in the location of the rectangle. The moment of inertia is not going to change. So what I will do, I will say this is the base position of the rectangle, and I'm going to call this side as the base and this side as the height of the rectangle. So what I do, I set up my integration. So as you can recall, the integration is going to be double integration, where say we are integrating with respect to y first. So the limits of y is going to start at y equal to 0 and go all the way to y equal to h. So we'll say that 0 to h, and limits of x are going to be x equal to 0 to, it will go all the way to x equal to b. So 0 to b. And you have your y square when you are finding ix equal to y square. I integrated with respect to y first, then I integrated with respect to x, because the density function is the constant function 1. So that's as simple as ix. So let's see how much we get. This is going to be integration 0 to b. Y square's integration is y to the power 3 over 3 with the limits of 0 and h, and then dx, and that is going to be integration 0 to b. I can take this 1/3 out, and if I put h for y, there will be also a constant, so I take out the h cube over 3. And I am integrating x dx. So you will get h cube over 3, dx is 1. So integration of 1 is x, and I get the limits 0 to b. So what I get? I get 1/3 b h cube as the moment of inertia. Similarly, I'm going to find the moment of inertia around the y-axis. So I will say iy is going to be, see, my limits are not going to change. It's still 0 to b, 0 to h. This time you're integrating x squared times density times dy dx. So what we get? When I'm doing it with respect to y, I get x squared y. And limits are 0 to h. Remember, I still have to integrate with respect to x. So this is my situation. If I put h, that's a constant, I can bring it out. So I'm integrating x squared dx with respect to x between 0 and b. And that is h times x cubed over 3. And I put in my values, and these are 0 to b. So I get 1/3 hb cubed as the moment of inertia with respect to the y-axis. So I'm interested in finding x bar bar, which is going to be square root of Iy over m. That reminds me that I should go ahead and find the value of the mass. So that, when calculated, again, your limits are still the same, 0 to b and 0 to h. That's just the density function 1, dy dx. So you get integration 0 to b, y, and the limits are 0 to h dx, which is equal to antiderivative of 0 to b, h is the constant, and I get h times x with the limit 0 to b. So this is b times h. So that's the mass. So now I get to say that x double bar is Iy over m's square root. So square root of, remember, Iy when found was 1/3 hb cubed. You are dividing by b times h, the mass. So that is going to be equal to square root of 1/3. H cancels and I get b squared. So I get b times square root of 1/3, which I can actually write as b square root of 3 over 3 units. So that's x double bar. Similarly, we're going to find y double bar, and we will get square root of ix over m. So that will be equal to, that was 1/3 h cubed b, and I'm still dividing by the mass bh. So I get 1/3. Again, you cancel the h and b, you get h squared. So this is h times square root of 1/3, which I'm going to go ahead and write as h square root of 3 over 3 units. So that answers my question.